I heard voices from somewhere. Record. Good. Okay, so current electricity. Oh, the recording missed my great pun. Oh, well. Current electricity. Today we have several topics, and I want to start out by a brief math check because I wonder if this is stuff that is in people's heads. And since I did it in the middle of the lecture, stuff had fallen out because the 3 o'clock was focusing on other things. Google question A, what's the area of a circle? Google question B, what's the diameter formula? Well, I'll write this down. Now D's nuts. Yep. Mm, 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 mm. I should say and because some people will think that is plus. Please note, this is my handwriting for and. Question mark. Let's have proper punctuation. Good, good, bad. What? Good, bad. Oh, you can write the squared. Cool. Oh, spoilers. Good, good, bad, good, 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 bad. What's N? Bad. No, good. Oops, I can't read. Yeah, it'll take me a second to process these. Chop chop if you're not done. If it's not perfect, that's okay. I just need to know. Good. I've got 11 mistakes. X? What's X? Hey, check which letters you're putting in what, yeah? The letter that I write next to the question is the letter I want you to put it in, yo. There we go. Okay, so more people don't know diameter than area. I'm surprised. Actually, a lot of you don't know what diameter is. Okay. Now let's check the proportional reasoning. Good. Proportional, good, mostly. Um, that's the answer. Good, good, good. Mostly good. And the last one. You don't just have to say increasing, decreasing, stays the same. You could say times 4, times 1, times 1/2. Last one is bad. Hmm. Eh. Okay, so let's go over these. Muy importante. These are foundations. Pi r squared. Cake r round, pi r squared. If you don't know this, know this. Get a tattoo of it and look at it all the time. I will not, I will not, what won't I do? I won't give you these answers on a test. This is 6th grade material. You need to remember it, revise it, review it. Diameter's formula, diameter is 2 times the radius. Diameter is all the way across the circle, radius is halfway across the circle. 2 pi r is the circumference, the fronts around. Area is the whole slice. Yeah, yeah, yeah. Now, let's reason about proportions. I don't give you x's. I don't give you y. Well, I mean, many of you have x's. You guys know the difference between x and y? X is someone you dated, a y is someone that, oh my God, why did you date them? Okay, so let's reason about this proportion. One way, the way that I demonstrated yesterday class to deal with this is to make up BS numbers and then say, how do they change? For instance, let's start by just saying if x equals 1, what's y? 2. Now, if x doubles, what's the new x? What's the new x? Look. If x equals 1, 2 over x equals what? 2. If x equals 2, 2 over x equals. So by what factor, what ratio have I changed what's new x over old x? 1/2. Let's do the same thing with squares. About a quarter of y'all just said it increases. You can tell me the ratio, the factor, not just bigger, and 10% said it decreases. Not just bigger, smaller. If I have x equals 1, x squared equals 1. If x equals, well, let's see, I say, by what factor does x change? X equals 2 now, x squared equals 4. What is the ratio of new to old? 4 times as great. It quadruples. By the way, that's not the same thing as exponential increase. This is power increase. Exponential is e to the x as a technical term. Questions about this? Okay, having perhaps refreshed some of this, now let's do actual physics. Okay, current electricity. Today I am going to discuss multiple terms. There will be many words, but the most important thing, the goal, the big goal, is that you take away what the heck is voltage and what the heck is resistance. We're going to be using voltage all the time for weeks and weeks, resistance for several weeks. You need to understand voltage and resistance by the end of this lecture. Well, You need to at least have a start on understanding. Your understanding, hopefully, will deepen and become more profound as we go on. In fact, I'm starting by giving an applied definition of voltage, how voltage is used in a circuit. When we talk about static electricity later, there is no circuit anymore. I will modify. I will give a more profound definition of voltage. But for now, let's give a more practical definition, okay? So one other note, if you're defining voltage, put voltage on top of your paper or whatever. Please note voltage has 15 different names. Well, 5 anyway. Voltage is called EMF, electromotive force. That's what it stands for. Potential, electric potential, and voltage. I'm sorry I didn't make up the names. It's not my fault. I blame Dr. Wagner. Not really, but just because. He's not here, so he can't defend himself. It's all his fault. No, it's the fault of the fact that we were investigating this stuff before we knew what it was. Electromotive force, it's not a force. Voltage isn't a force. It is not newtons. It does not equal to the push or pull on electrons. But it is what causes the electrons to move in a circuit. So way back when, we didn't really know what was going on. We were building this up and people thought, what moves the electrons around? Let's think of it as a force. It's not. Potential, muy importante. Last semester, we talked about potential energy. Electric potential, voltage, is not energy. It's intimately related, but not the same thing. Later, we'll talk about electric potential energy. Electric potential, voltage. Electric potential energy, energy. Okay? Now, here's my definition. My defining idea for voltage in a circuit is you get or lose this much voltage as current flows through given component. Energy lost or gained divided by how much charge is losing or gaining that. So as electricity flows through this, that, or the other component, it is the ratio of how much energy is lost or gained. It'll be gained in a battery, lost in everything else, to how much charge is losing or gaining that. It is the energy divided by the charge. Nah, let me be precise. It is the change in energy divided by the amount of charge. As an equation, if you like, we can write the change in voltage, the difference in voltage from place to place is how much its energy changes per amount of charge feeling it. I wrote cube before. 1 volt is therefore, what's the unit of energy? What's the energy of charge? 1 volt is equivalent to 1 joule per coulomb. If you see that, that's not common to see. Now let me give multiple qualitative, multiple intuitive analogies for voltage and try to make some sense of this mathematical definition. Do you know how to find Q? Well, you could measure the current and find out current times time would give you charge. Or you could simply say, intuitively, I've got some charge in the circuit. This is the ratio of how much energy this charge has to how much charge there, how much energy this charge has divided to how much charge this charge has. It is the share of energy that each electron gets, each coulomb worth of electron gets, to be precise. What's per capita income? What's per capita? In economics. You guys know per capita? Raise your hand. No one's taken an econ class? One person? What's per capita? What? Yeah. Well, there's the Latin. Money, yeah, money per time period. No, not time. There's nothing to do with time. And no one's taken econ and knows per capita income? Okay, screw it. I'm not going to make a connection to stuff you don't know. Chemistry class, who has calculated the calories per mole of for a reaction, calories per mole? Raise it higher. I can't see. Many of you have calculated, but only a quarter of you have calculated calories per mole. Calories per mole is intimately related to voltage. What does calories per mole tell you? If you've got this many reactions, how much total energy is released? It is the energy per reaction, per mole of reactant, right? That's the essence, the idea behind voltage. Okay, now 3/4 of you haven't taken that class or forgotten that concept. So let me give another idea. Voltage is pressure. Voltage is how much you suck on a straw to drink something, right? How do you drink? Don't you expand the volume of your airway, right? Expand the volume of your lungs, which decreases the pressure, PV equals nRT. Decrease the pressure inside your mouth, and there is what? There is a pressure difference between the liquid on the other end, your milkshake, and your face hole, right? What happens when there's a pressure difference? There's a flow, right? Everyone's had milkshake before or water with the straw? Hey, think about this again carefully. Here's a very important thing about voltage. If I've got 15 pounds per square inch on one side of a straw, atmospheric pressure, and 15 pounds per square inch inside my mouth, is any liquid going to flow? But there's 15 pounds per square inch. Why doesn't liquid flow? They balance out because what would you say? There's no difference. Pressure itself doesn't do squat. Only differences in pressure from one place to another cause movement or flow or whatever. Just having pressure doesn't cause flow. It is when there is a difference in pressure, a change. I mean, it causes a flow. I don't think they're equal. But yeah, you could, in meteorology, in understanding weather, weather patterns, where does wind go? Well, from high pressure zones to low pressure zones, right? You understand, see that on the Weather Channel. Wait, does anyone still watch Weathermen on the TV anymore? No, of course. Back in the day, there used to be things called weathermen or meteorologists on television, but that was in the olden days before you guys were born. They had TVs when you were young, TV channels. Whatever, I'm getting super distracted. Let's ADD back on topic. And pressure is not the thing that drives flow. It is a change in pressure. And that's the delta here. Voltage itself don't do nothing unless voltage is changing. Did you know that you could hang from the transmission line of a 500,000 volt electric line? Did you know this? You can dangle from that and get no electric shock as long as your feet aren't grounded. If your feet are grounded, this is 0 volts, this is 500,000 volts, you can be Kentucky Fried Chicken real fast. Yeah? If there is a difference in electrical pressure, voltage, from one side of you to the other, that's what causes current to flow. Just to having a pressure, nada. Just having a pressure as long as it's the same. Yeah, please.
Formula, we can say that if there is a difference in the number of electric charges on the two ends of a wire, then the
electricity that's flowing through it will lose that amount of energy per coulomb of charge.
That is what is called a 1 volt.
Yeah, exactly. Now, in a wire, I will warn you that wires have very low electrical resistance, and it takes a hecking lot of current before you drop any volts in a wire. So in most circuits, I mean, a transmission line, a long distance transmission line from a power plant to a city or whatever, then that actually becomes important. You do lose a significant amount of energy when the voltage is lost from one place along those long lines along the wire. For the most part, most of the time in this class, we're going to assume that the voltage does not change along a wire, only in a battery and a resistor. Okay, one more analogy, I swear, and then we'll move on to slide 3. Okay, the last analogy is voltage is the difference between, let's just pretend everyone is a complete communist, okay? Right? Electrons are super commies. It is the difference between China and Switzerland. Which economy is bigger? China, it's the second largest in the world, right? Or is it the first largest? Did it beat us? Whatever. China's the biggest economy in the world, but it's got 1 billion people. Switzerland is they're medium-sized economy, but they're what? How many Swiss people? Like 100? 15 Swiss people, right? The average, the amount of money per person, Swiss people swanky, assuming that everyone was actually equal. You could say the average Swiss person, the Swiss per capita, that's what per capita is. The Swiss are richer on average than the average Chinese person. Again, if we actually shared evenly. Humans are terrible at sharing equally. Electrons are great at sharing equally. The energy that each individual electron gets at a point in a circuit is really the same as every other electron's energy. That energy changes as those charges flow through the circuit, but like at a given place, you got 2 electrons next to each other, they have the same fraction of the total energy, the same voltage. Okay, I hope that at least one of those analogies clicked, because we're going to be using this left, right, and center. Hey, real fast. I've been talking a lot. Google question F. What are the physics units? Kilograms, meters, seconds, amperes, volts, ohms, joules, blah, 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 of EMF. Hit enter. And this is F, by the way. The units of volts cannot be joules per volt. The units of volts can't be defined in terms of itself. Okay, I got 90% of you there. Let me go back to the previous slide and say that voltage is EMF. Voltage and EMF are the same thing. Also, electric potential is the same thing. The units of voltage are volts. The units of EMF are volts. All right? If you see a reference to EMF, that's voltage. It's measured in volts. Okay. Now, before I go on to this slide, I have a word of context, a word of warning. The equation I am about to present is super important. It is not a universal truth. I am going to connect voltage and current in one kind of component. Every component, every different kind of component has a different relationship between voltage and current. There's a different V equation for every single electronic component. The meaning of voltage is always joules per coulomb. That's a universal truth. That's a definition. But if we have an equation for V versus I, every single component has a different one. I don't want to see you writing down IR when talking about a battery, or a capacitor, or a transformer, or an inductor, or a transistor, or whatever. V equals IR applies when there's an R. An R stands for resistor. Well, R stands for resistance, but when you've got a resistor, that's something that has a resistance. And that you can apply V equals I times R with. I'm going to define resistance as the constant of proportionality. The idea is that voltage is proportional to current. Oh, I didn't check this. What's proportional mean? Not equal, not the same. It says very close. The ratio is what? The ratio is fixed. The ratio is constant. A divided by B does not change. X over Y is constant. As an algebra equation, Y equals mx, not mx plus b. The way I say it for non-college students is as x doubles, y doubles. As x triples, y triples. As x divides by 10, y divides by 10. Yeah. Okay, so that's important because when do you have zero current? How much voltage do you have to apply to get zero current? You have to apply zero voltage to get zero current. If it's a proportionality, that means there is no minimum voltage to get electric current. Not in a resistor. In a resistor, you can apply any amount. You can make the voltage smaller and smaller and smaller and smaller. And resistor, oh my goodness, I just smashed my bone pastry. Resistors don't stop electricity. Resistors limit, resistors throttle, resistors uh, 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 cut down on the electric current, but they don't stop it, okay? It's called the resistance, not the stoppance. Write that down, know that. Meditate upon this. The equation delta V equals R times I says that you can make V as small as you want. Unless it's zero, there will be some current. This is called Ohm's law, which is, as usual with electronics, a shitty name. Ohm's law is not a law of nature. It is a general tendency, which is true, for some materials, for metals, for resistors. Yeah.
When there is a difference in the electric potential, right?
Yes,
So when
that is voltage.
so when that V is zero, why would the current pass? Even the
It won't. It won't. If you have a wire where both ends are pressurized the same, there will be no flow. I mean, like think of a straw with atmospheric pressure on one end, atmospheric pressure on the other. Is water going to flow through it?
why
Or air?
wouldn't the resistor stop the current?
It doesn't stop it. It doesn't stop it. Unless you got infinite resistance or zero voltage, current will be something. Good questions. Other questions? Okay. So Ohm's law, Ohm's general tendency for some materials, says that there's a relationship between voltage and current, and that relationship in a resistor is the resistance of the material. I would like to divide both sides by I and think about what this means. What is volts per amp? Volts per amp tells you how hard you suck to get a decent mouthful of soda, right? How hard do you have to pull with your mouth to drink at a reasonable rate? Yeah? The pressure difference per gulp. Resistance is, are we talking about a cocktail straw or a normal straw or a boba straw or drinking through a garden hose? Ew. That's resistance. Hey, what's the difference, by the way, between a cocktail stirrer and a normal straw and a fire hose? What's the difference there? The diameter, the size. Resistors aren't hollow tubes. What resistors are is hollow tubes filled with a sponge. Okay, what would happen if you filled a straw with a slightly spongy material? Secret. Yes, that's what I'm doing right now. I'm trying to get the relationship between voltage and current and make sense of it. Okay, so the voltage, the pressure it takes to get a decent gulping of your milkshake, of your soda or whatever, that's how much the straw is opposing it. If you suck a little, by the way, you'll still get some liquid into your mouth. If you really hard, you'll get more, but there's no pressure difference that you apply that you get zero milkshake or soda. Straws don't have stuff inside them. In electronics, resistors do have a material that they're made out of, and that material gets in the way. What determines the opposition of flow in a straw? Its size, its shape, right? Its cross-sectional area, its length also, although you guys probably don't know that because we don't use straws of different lengths. Okay, size and shape. With a resistor, there are three factors that matter. Resistance is from three factors. Write this down: length, area, and material.
So for that equation, so the current with the change of voltage,
What? Current does not change in voltage. Voltage is change in voltage.
like for the equation that's because it says current over through that resistor, right? Or is that not a slash in the first thing?
No, no, that's an I. Current is I. Oh my goodness. Thank you. That's muy importante. No wonder that's, yeah, oh, yeah. This is an I, current I. Ay, ay, ay. Thank you. Other question, yeah. Well, I buy them for 5 cents from Mouser.com. It's an electronic component that you buy. You can make them from wire. It'd be tedious. Yeah, yeah, and I'll call it a resistor. Wires also carry some resistance. Like I was saying to Harshad earlier, the resistance of a wire is much, much smaller for most practical purposes, much, much smaller than these packaged resistors you just buy. So what? So if I'm talking about a circuit, we're going to assume that the wires are perfect conductors of electricity. You guys have heard about this at grade school, conductors and insulators? Insulators are things with huge, enormous resistance. Conductors, the better a conductor, the lower its resistance. Yeah? Okay. Does this statement make more sense now that you know that's not a slash? The proportionality between the current and the voltage and the current? As voltage doubles, current doubles, and so on? Great. Here's that relationship. I said verbally it depends on material, length, and cross-section. Here's the equation to calculate it. I'm going to write this down. I've got a couple of words of wisdom about common mistakes in a second. Rho, it's the Greek letter rho, not that you can tell. We do use the same letter for multiple things. Sorry. But I mean, context. It is like very, yeah, it's analogous. It's absolutely analogous. You got a denser sponge, you got more resistance to flow. But no, in this context, in electricity context, rho resistivity is not the same thing as density. It's a good analogy, though. Okay. I want to emphasize a couple of muy importante points. First off, resistance is not resistivity. Resistivity is a material constant that you look up in a book. Resistivity don't change unless you change the temperature. It is temperature dependent. MCAT students, you'll learn how to calculate the change in resistivity versus temperature. For our purposes, I'm not going to include that in this class. In PHY112, you could treat resistivity as a constant that's just based on, do you have iron, do you have copper? Do you have steel? Right? You look it up. I will give you a table perhaps if I ask you a question to calculate with resistivity. And if you don't have the table, you can't solve this problem. You can't plug in numbers. Resistivity is based on the material, and it's something that is just God-given or professor-given. Oh, I don't have tenure. I know I'm not God. L and A, length and cross-section of the resistor. I mentioned at the beginning, half a second, I mentioned at the beginning, all resistors that I've ever seen are roughly circular, cylinders, yeah? Question?
In the formula, why
True?
fixed object?
Yes. When I buy a resistor for 5 cents from Mouser.com, its value is printed on the side of the resistor in a special code. That value doesn't change. It can't. And okay, if you heat up the resistor, yes, its resistance, its resistivity, therefore its resistance do change, yes. But resistors are also designed to minimize that effect. Practical resistors. Okay, so actually, Harshad X, his first question goes to a very important point. If I change voltage, does that change resistance? I got a yes and I got a no. Argue. If I change voltage, does that change resistance? You say yes. Why? Argue. Huh? You say no. Why? Yeah, why? True. True. The material doesn't change, the length doesn't change, the area doesn't change. This formula says no changey. Well, hold on though. We got a formula that says V equals IR. How can V change and R not change? I changes. Yeah? V equals IR doesn't mean V changes, R changes. It could be R or it could be I. If you've got a given resistor, a physical resistor, its value is printed on the side. That value is its value, is its value, is its value. It does not change. Except for heating, which we're not getting into. My biggest point here, this is a good formula. It's a great formula. Yeah, love it. Yeah, whatever. My biggest point here is resistance of a resistor is a property of the resistor, not the electricity flowing through it. Do not think V equals IR means that V controls R. V controls I in a resistor, in a given resistor. Right? You can put different resistors in, and then you'll get a different current for different voltages. You could change the resistor, but if you've got a given resistor, a given 5-cent part that I bought, whatever, R is set, cannot change. Right? Okay, I've been talking a long time. Let's do some questions. Let me see what you're picking up from what I'm laying down. Call these A, B, C, D, E. And you could put one or more if you believe that there are one or more correct things. Oh, for God's sake, this is Google question G. See what I'm asking? It's a multiple potential answer question. Oh, I just love correct answers. Oh my God, so many correct answers. I'm so happy. Shoe? Oh, can't read. Hey, turn to your neighbor and tell them the last thing I just said 1 minute ago. Because I did literally just tell you the answer to this question. All right, but not great. I want to go for great. I want to go for great. What did I just say? What was the last sentence I said? Yeah. Okay, question first, then. So for Google question G, if you think the answer is length and type, you would say AB. Yeah. Okay, so again, let me remind you what I just said. The last sentence I said is the electricity doesn't control the resistance. The properties of the resistor control the resistance. Voltage and current don't control R. The relationship between voltage and current is set by R. So what does that mean? What's the answer? ABC. Voltage and current do not change the resistance of a resistor. They can't. If voltage changes, current will change. If current changes, voltage will change through a given resistor. You smell what I'm stepping in? You? Okay, read carefully. Google question. You can and should work together, perhaps, on this one. Read carefully, my friends. Okay, my point is not to trick, by the way. When I give a hard question, my point is not to trick you. It is to force you to confront something. This is a question that forces you to confront something. What does resistivity depend on? The material. The resistivities are the same. One. I reserve the right to give you extraneous information. Just like in every single thing in the real world, there may be additional facts that you do not need. Do not think that just because a number appears at a problem, you have to plug that number in somehow. Does the temperature vary? You're absolutely right that changing the temperature does vary, but I'm also promising for our purposes in this class, I'm never going to give you varying temperature. Good question. Gina, yes, absolutely. Doubling the diameter increases the area by a factor of 4. Good. Reduces resistance. But what did I ask in my question? I did not ask about resistance. I asked about resistivity. Go back to the last point here. They are different things. Okay. So now, here's the questions you thought I was asking. Half of you thought I was asking. Now I ask you for the ratio of the resistances. If I double R and I double D, what happens to, if I double D and I double L, what happens to the fraction? Remember how I guided you at the beginning? I answered proportional reasoning before. You can make up BS numbers. Let me remind you of the formula. I can let you guys go early too. We don't have that much more. Have hope, my friends. Have hope. Who's utterly, completely screwed and lost? How many have we got? Utterly dead? Dead in the water? Okay. I'll give hints then in 1 minute. I'll walk you through part of it in 1 minute. Yeah, Gina, I know, I get it. We're gonna practice this skill, reasoning about proportions, many times in this course. I think it is one of the more powerful lessons I can give you that'll actually apply to your real world. I get it. It's hard at first. Okay, hint time because we've only got about 25% correct. A little more than that. Hint time. Here's how to reason about just the effect of the area. I tell you about D. D doubles. Okay, I've got a formula, R equals D over 2. If D doubles, what happens to R? Well, one way to think about this is to make up any BS number whatsoever. D is 5. 5 halves, 2.5, right? 2.5. Now D doubles. Now what's D? 10. What's 10 halves? What's the change then from 2.5 to 5? By what factor have I increased? 2. I doubled. If I double D, I double R. Note, the over 2 is irrelevant. Constant coefficients do not count when we're considering proportions. Make up a different number. Maybe this only works for 5. No. Suppose D is 2. What's 2 over 2? Now if I double 2, I get 4. What's 4 over 2? So diameter went from 1 to 2, yeah? Great, let's make up a number for here. I know that if D doubles, R doubles. Great, now what happens if R doubles, what happens to A? We did this at the beginning of class. It quadruples. Here's how to do it with my BS number system. Let's say pi equals 3. Pi equals 3, R equals 1. What's A? You can plug this in. Pi equals 3, R equals 1. What's A? Google form! If pi equals 3 and R equals 1, what is pi r squared? Google form J. If pi equals 3-ish, I was the answer to this that 75% are missing. I'm building up to how to do this. Giving you the skills to pay the bills. Again, I wish you to plug in pi equals 3 and r equals 1 and evaluate this expression. Okay, my dudes. 3 times 1 squared. What do we do first? Do we multiply or do we exponentiate? PEMDAS says we exponentiate first. What's 1 times 1? What's 3 times 1? 3. Okay, refresh yourself on PEMDAS if you need to. So we go from area equals 3 to, if I double R, what happens to A now? A becomes, Google it. Not Google it, for God's sake. Question K, Google form it. If I double R, now what's A? Assume pi equals 3. I'm a physicist, we round. Not as many right as I want. This is K. J was if R equals 1, what is area? Assume pi is 3. Now I'm saying if R becomes twice as much, what is our new A? And yes, let pi equals 3. Okay, so here's how to do this. If r doubles, that means r equals 2. If I say 3 times 2 squared, what do I do first? This becomes 3 times 4, which at the last time I checked is 12. Yeah? What happens to area if radius doubles? It quadruples, eh? Right? Pi is irrelevant. Constant multiples are ignorable when we're reasoning about proportions. R squared, if I double any number, then square it, the doubling squares. I get 4 times as much. Again, if I double a number, then square the result, I've got 4 times as much because the double, the factor 2, becomes 2 squared as much. Great. Now the last question in guiding you through this, if A quadruples, by what factor does resistance change? What is the ratio of new to old if A becomes 4 times as great? Put in the Google form, Google question L. Think carefully. New divided by old, if A becomes quadrupled, 4 times as much. New divided by old, by the way. To say 5 is to say that the new resistance is 5 times as big when area is 4 times as big. Yeah, we can practice this. This isn't okay. Again, what I am asking, my question is, I wish you to plug in this formula, rho L over A, if area becomes 4 times as great as it was, which is, I'm building you up to solving this original problem. If area becomes 4 times as great as it was, what happens when you quadruple a denominator? What happens to the fraction? You don't have to just say goes down, comes up. I want a ratio. I'm not telling you what rho and L are, but if I go from 1 downstairs to 4 downstairs, have I gotten bigger? If I'm dividing into 4 times as many pieces? No. The answer is not 4. It is 1/4, 1/4. Okay, the correct answer here is if you increase the denominator by 4, a factor of 4, the fraction becomes this quarter as great. I have now showed you how to reason about half of this problem, the hard half of this problem. I just showed you how to calculate, to predict, to understand if diameter doubles, the resistance does what? Quarters. Now what happens if diameter doubles and length doubles? Google question M, the final question for now, is if you double something and then quarter it, by what factor have you changed? What is the ratio of new to old? Please note, 2 means doubling the quantity. 1/2 means halving the quantity. Again, I'm going to double something and then I'm going to quarter it. What is the ratio of new to old? What? What is the ratio of new to old if I double something, then quarter it? The question, one more time, is, I wish you to solve the original question one more time. I give you that the wire is 2 is twice as long. L becomes 2L. And as twice the diameter, we have exhaustively found out that area quadruples. What happens to a fraction if you double the upstairs and quadruple the downstairs? What is its ratio now? New divided by old. Okay, let me go back to my BS method, BS number method. I give you $100. Okay. Now I double it. How much have you got? Then I quarter it. You have a quarter of 200. What have you got? Please tell me you can find a quarter of 200. What do you got? 50. Yeah, right. How much have I got compared to the beginning? Is it 8 times as much? Is it half as much? Is it a tenth as much? What is 50 compared to 100? I've got half as much as I had. Okay, we can practice this. This will become, this is a very important skill, I believe, that everyone needs to be able to do. Reason about numbers, not just plugging into a calculator. Where are we at? 7:39, 7:39, 5:39. We're gonna stop for today. We'll pick up here, same slide set next time. I love each and every one of you. Adios. Only if you promise to do the same.